Our speaker is James Sowers from the University of Minnesota Duluth, who is going to speak about integer partition statistics. Please.
Mel, thank you so much, and thanks to all of you who are here today. Let's go ahead and get started. I'll just really quickly on the title slide mention that I'm going to spend time today talking about integer partition statistics, relationships between the crank, something called the minimal excludant, which is often called the MEX, and then a very new idea called partition fixed points, which I'll bring up in the latter half of the talk. Let me begin by thanking Mel for the opportunity to share this talk today. It's great to be able to do so. And I also want to take the time to thank my co-authors, Brian Hopkins, who's at St. Peter's University in New Jersey, Dennis Stanton at U of Minnesota, and Ezai at Penn State. This work has actually appeared in the last few years in 4 papers. The first was with Brian Hopkins that appeared in the American Mathematical Monthly, a nice small paper where we proved our first significant result, and I'll show you that result in a few minutes. And let me pause and just give Brian some extra kudos, because really deep down, he's the one who pulled me into this topic and really discovered some wonderful things which we have now pushed through, and we continue to discover more and more. But Brian really was the person who started all of this. Then Brian and I joined up with Dennis Stanton and published a paper in 22 in the JCTA. We then published another paper in 22 with Ezai in the Electronic Journal of Combinatorics. And just within the last 1 or 2 months, Brian and I published another paper in Discrete Mathematics, and all of these are on these partition statistics and the relationships that we found between them. So what I want to do today is tell you about those relationships. I'm going to show you these connections between the crank. By the way, I'll define the crank as well, the MEX, and these partition fixed points. I'm also going to take a couple of small detours, sort of number theoretic detours into properties of the MEX or the crank or both. And I'm just going to point out that the initial work really involved generating function manipulations, which is where I am most comfortable. And then our later work with, I should tell you what HS and HSS stand for. HS is Hopkins-Sellers, HSS is Hopkins-Sellers-Stanton, and HSY is Hopkins-Sellers and E. Brian and Ezai are very, very talented people on the combinatorial side, on the bijective side. And so that paper that appeared in the Electronic Journal of Combinatorics was much less about generating functions and much more about combinatorics and bijections. Okay, so I'm going to talk about partitions today. Let me just remind you what partitions look like. So if n is equal to 4, I'll often refer to the value of the sum as the weight of a partition. If I take all the partitions of weight 4, then these are the 5 partitions that you get. And I'm guessing that many of you know that we want to write these parts in non-increasing order. So the largest part's going to be on the far left, and then we'll write them in non-increasing order as we read left to right. If you want all of the different permutations possible, then you're looking at compositions, not partitions. So we're going to look at partitions today. We're going to define the function P of n to count the number of unrestricted partitions. And so P of 4 is equal to 5 because there's 5 partitions in the list in the middle of the page. Okay, so that's our sort of initial place where we'll be doing our work today. And the story really begins with Srinivasa Ramanujan. This is his famous passport photo, which was taken within 1 or 2 years of his passing away in 1920. And Ramanujan proved in the late 19 teens that this P function that I just defined a few moments ago satisfies three very interesting congruences. One, a divisibility mod 5, one mod 7, and another divisibility mod 11 in these arithmetic progressions. Now, I have to tell you that I actually have spent most of my career studying these kinds of divisibility properties. And those of you in the audience who have watched my talks in the past know that I often give talks where I discover and prove these kinds of divisibilities. That's not the goal today. And yet, this is the starting point. And there's a reason that this is the starting point, which is this. Ramanujan in the late 19-teens proved these results using generating function manipulations, and in the process, single-handedly began the study of partition function congruences, which goes on today. But 2 or 3 decades later, a number of mathematicians wanted to be able to combinatorialize Ramanujan's proof or Ramanujan's results. And what I mean by that is, take the P of 5n plus 4 divisible by 5 fact. What people said was, well, if that's true, then we should be able for any n to take the partitions of 5n plus 4 and do one of two things. Either be able to put these partitions into packets of size 5, or put them into 5 equally sized packets in a natural way. And that natural placement of the partitions would then imply the divisibility by 5. And of course, do something similar for 7 and 11. And in 1944, one of the first attempts at doing this was made by Freeman Dyson when he was in just in his early 20s. And in a paper in Eureka, Dyson defined a partition statistic known as the rank, which is pretty easy to define. It's just the largest part minus the number of parts in that partition. And what Dyson, so let me just show you what Dyson is trying to do, and I won't dig into this table too much, but let me just point out what's happening here. If you take n equals 9, which is of the form 5 times 1 plus 4, so it's in the arithmetic progression 5n plus 4, there are exactly 30 partitions there. And what Dyson was able to show with this example was that if you took all the partitions where the rank was 0 mod 5, there would be 6 of them. If you take all the partitions that are 1 mod 5, there's another 6. And there's another 6 for 2 mod 5, another 6 for 3 mod 5, and another 6 for 4 mod 5. And so the idea was that the rank would be able to handle the mod 5 congruence of Ramanujan. And in fact, it's been proven that the rank actually does handle the mod 5 and the mod 7 congruence of Ramanujan, which is really extraordinary, but it fails to handle the mod 11 congruence. In other words, you can find values of n within this arithmetic progression that's 6 mod 11, such that the partitions do not get pushed into 11 equinumerous sets. And so the rank failed Dyson in that sense. So in the same paper, Dyson makes a bold conjecture. He says there must be another statistic, which he called the crank, which had to exist, and it would have to prove this mod 11 result the way the rank handles the 5 and 7 results. Dyson didn't claim he had an idea what this thing would have to be. He didn't have an idea how to define it, but he certainly claimed that it would have to have certain properties, which eventually were proven to actually be true. So that's 1944 when Dyson makes this conjecture. And 44 years later, George Andrews and Frank Garvin, whose images are here on the screen, published their work that proved that such a crank exists. And I'll just gentle bit of history here. Frank Garvin was one of George Andrews' PhD students at Penn State, and I think he finished his PhD around 1986. So clearly the two of them had a lot of time together in the mid-1980s, and in 1988 they published their definition of the crank. And in their paper in the Bulletin of the AMS, this is what they defined the crank to be. So let omega of lambda be the number of ones in the partition lambda. So how many ones do you have as parts? and let mu of lambda be the number of parts in the partition greater than the number of ones. And then the way they defined the crank was this. If there are no ones at all, just let the crank be the largest part. That would be lambda 1 in this notation. And if there are some ones as parts, then the crank of that partition is going to be the number of parts greater than the number of ones minus the number of ones. And what Anders and Garvin proved is that that crank that I've just defined for you there does handle Ramanujan's congruences mod 5, 7, and 11, I'll say simultaneously, if you will, in the same way. And so they handle this question that Dyson requested or asked in 1944. So for example, really quickly, the crank of something like 6 plus 5 plus 4 plus 3 plus 2, well, that's just equal to 6 because there are no ones. The crank of 5 plus 3 plus 3 plus 1 is this. How many parts are greater than 1 because there's 1, and you can see there that there are 3 parts that are greater than 1, minus the 1, and 3 minus 1 is equal to 2. Okay, so that's where the 2 comes from. And here's one last example. Notice that there are 3 ones, and there are exactly 2 parts greater than 3, the number of ones, and those are the 4 and the 4. So you take 2 for the 4 and the 4, minus the 3 for the number of ones, and you get -1. I wanted to show that example to show to you that the crank can actually be very naturally negative as well as positive. And of course, we can also rig it to be 0, which will be important for us a little bit later on. Okay, so we'll come back to the crank in a second. For now, let me define the MEX, or minimal excludant of a partition. And basically, the minimal excludant is very easy to define. It's just the smallest missing part of the partition, and every part's got to be positive. So the MEX is going to be 1 or larger for every partition that you write down. So for example, the MEX of 53331 is 2. We have a 1, but we don't have a 2, so the MEX is 2. Here the MEX is 1 because we're missing a 1, and that would be the smallest part we could have. And here we have some 1s, we have some 2s, we have some 3s, we have some 4s, so the MEX here is equal to 5. Right, so we have the crank statistic that I've defined a moment ago. We have this MEX statistic, which looks rather different from the crank. And what we want to do now is talk about how these two can actually be related to one another in what is probably a priori not the most obvious way. So let me do that now. So I'm going to define 2 functions, little o of n to be the number of partitions whose MEX is odd, O for odd. And I'm going to define E of n to be the number of partitions of n whose MEX is even. Clearly, P of n, the number of all partitions of n, is equal to O of n plus E of n. That's obvious. And now I want to look at 2 important generating function results. And it's this result, this fact I'm about to prove to you, which is the fact that's in the paper with Brian Hopkins in the American Mathematical Monthly. All right. So to do so, I need the generating function that Frank Garvin published in the late 1980s. For the function capital M of little mn, and that is the function that counts the number of partitions of weight n where the crank is exactly m. And Frank proved that this is that generating function. I just want to stare at it with you really quickly and say 2 things. One is that this factor in front of the sigma symbol on the right-hand side, 1 over q sub infinity, is exactly the generating function for P of n. Okay, so it's kind of natural that that's there. And the other comment I want to make is that this m, which is the value of the crank for every one of these partitions, only appears right there. So you have a generating function where the m plays a role, obviously, but it doesn't play a very big one, right? So that I just wanted to point those 2 things out now. And now let me just tell you what I want to do. I now want to take that generating function, and I want to find a generating function for the number of partitions of n where the crank is non-negative. That means I want M to be greater than or equal to 0, because M is the crank. So I'm going to take this generating function that's in front of you right now, and I'm going to sum on the left-hand side from M equals 0 to infinity, which of course means I'm going to sum the right-hand side. M goes from 0 to infinity as well. And that's going to give me a generating function for all partitions of weight N where the crank is 0 or greater. When I do that, if you think about it for just a moment, the sum on the right-hand side from M goes from 0 to infinity can be pushed all the way to the end, if you will, where that one little M existed in the exponent on Q, and all the other stuff can go to the left of that sigma symbol. And the absolute value of M that was on the previous slide can now just be written as an M, because all of these M's are greater than or equal to 0. And I'm sure you folks all know that that's just a geometric series. And now I see that these two things will actually cancel, and I will end up with a really pretty generating function here, which I've now put in red only because I want you to remember it a little bit more. 2 comments. You still have the generating function for P of N sitting in the front. That's the 1 over Q infinity. And you have an alternating series over L. And that's important. I'm going to come back to the fact that that's alternating in just a moment. So you have some sort of inclusion-exclusion going on here in this generating function, if I can say that in a bit of a loose way. All right, so that's now the generating function for all partitions where the crank is non-negative. Okay. Put that aside for a moment, and now I want to go look at the MEX, and I want to look for a generating function for all of the partitions of N where the MEX is odd. That was O of N. Now let's think about what this looks like for just a minute. If the MEX is odd, let's say that that MEX is of the form 2n plus 1. So 2n plus 1 is the first non-part. In other words, that's the smallest thing that doesn't appear as a part, okay? How do you write that generating function? So the 2n plus 1 is not there. That means you must start by multiplying by q to the 1, q to the 2, q to the 3, up to q to the 2n to guarantee that a 1 shows up and a 2 shows up all the way up to a 2n. And then this denominator is basically handling the generating function for all partitions of N, except we have excluded the 2n plus 1 because it's serving as the minimal excluded part. Okay, cool. And we do that for all N. So now we're doing it for the part 1, the part 3, the part 5, etc., as we take the sum over all N. If we now then multiply that 1 minus q to the 2n plus 1 into the denominator and into the numerator, then the denominator just becomes q sub infinity, and the numerator can be written as it is, and all I've done there really is throw in that 1 minus q to the 2n plus 1, and I've taken 1 plus 2 up to 2n and written it as this triangular number 2n times 2n plus 1 over 2. And now this is just equal to this when I distribute that q power into this piece in the numerator. But if you stare at that long enough, you realize that those are really the same series. It's just that one of them goes 2n times 2n plus 1, and the other one goes 2n plus 1 times 2n plus 2. And the ones that start with the 2n plus 1 times the 2n plus 2 in the exponents have a minus. And so I can rewrite that as a single sum like that. And that I put in red because it's identical to the other thing that was in red just a slide or two ago. So what have I proven? Well, what I've proven is that the number of partitions of N with non-negative crank, this function that Garvin and Andrews defined, equals the number of partitions of N with smallest missing part, or MEX, that is odd. I have to tell you that a priori, when Brian first sent this to me and he said that he had somehow discovered this computationally, I was floored. I had no reason to believe this had to be true, but of course the generating function proof gives it to us. So that's a really, really cool result. And again, I want to be clear. I'm not saying that the two sets of partitions are identical. I'm simply saying that I can put them in bijection with one another for any weight n. It turns out that this proof, or this result, not this proof, but this result also appeared in a paper of George Andrews and David Newman in the Journal of Integer Sequences, also in 2020. Brian and I were unaware of this, but we ended up almost simultaneously publishing this result. So there's an obvious corollary then. So think about this for a minute. That's all the partitions with odd mechs. Can we now count stuff for even mechs? Well, of course, the even mechs then must be equinumerous to the number of partitions of n with negative crank, because that's the way these things split up. But it turns out that one can say something even more cool, namely that the partitions with even mechs of weight n are equinumerous to the number of partitions of n with positive crank. And here's the result, and this is true for any n greater than 1. So as I just mentioned, the number with even mechs, that's E of n, must be the number with negative crank. This is true because of the way we've partitioned the set of partitions of weight n. But it turns out for n greater than 1, you can very easily see that the number of partitions with crank m equals the number of partitions of the same weight with crank negative m. Go back to Frank Garvin's generating function for capital M of little mn. And if you remember, the little m was in absolute value symbols. And so you can easily make this statement as long as the lowercase n, the weight, is at least 1. And so the number with negative crank, truly negative crank, must be equal to the number with truly positive crank as long as the weight is 2 or more. Okay. Well, in a paper in 2019, which was a bit of a motivation, I think, for Brian's work, his computational work, the paper in the Ramanujan Journal, Shen proved via some fairly extensive Q-series manipulations that O of n minus E of n must be greater than or equal to 0 as long as n is bigger than 1. Let me show you a table to motivate this. So remember, O of n is the number of partitions of n with odd mechs. E of n is the number of partitions with even mechs. If you take O of n minus E of n, it's clear that these numbers are positive as long as you start at n equals 3, and they're growing, and they're going to keep growing as well. Well, thanks to what Brian and I had proven, we could actually give a combinatorial interpretation of O of n minus E of n. O of n is going to be the number of partitions of n with non-negative crank, and E of n is the number of partitions of n with positive crank. So that difference is exactly the number of partitions of n with crank 0. And so all one has to do then is show that you can build crank 0 partitions. And of course you can. In fact, if you just take the partition with 2 parts, n minus 1 for one part and 1 for the other part, as long as n is bigger than 2, you'll have 1, 1, and the n minus 1 will be bigger than 1, and so you'll have one part bigger than the 1, 1. 1 minus the 1 gives you 0. And so you know that you have to have some crank 0 partitions as long as the weight of the partitions is at least n equals 3. And so we were able to prove Shen's inequality in a beautiful way, in my opinion, a very nice interpretation of O of n minus E of n. Okay, so let me shift gears now really quickly, because eventually what I want to show you today is a theorem that basically says something like all of the following things are equal. I don't know if any of you've seen these theorems in like linear algebra books where it says the following are the same, the following are equivalent, right? This matrix is invertible, its determinant is not equal to 0, and there's like 15 different things. Well, I'm not going to show you anything that long, but I do want to get to a place where I can show you a variety of connections. And so I'm going to take us down a slightly different path just for a moment, and talk quickly about the Frobenius symbols. Let me show this to you pretty quickly. Take a partition. Here I've given you the partition 6, 4, 3, 3, 2, 1. The Ferrer's graph of that partition can be drawn this way. Each row has the number of dots that correspond to a part. So there's 6 dots in the first row, 4 dots in the second row, 3 in the next, 3 in the next, 2 in the next, and 1 in the next. So I read these by rows. That gives me what's called the Ferrer's graph. Now, what I can do with that is the following. I'm going to take the main diagonal, and in this case, I've left those dots black. I have marked the dots to the right of that main diagonal red, and I've marked the dots below the main diagonal in blue. And now what I do then is I build a 2-rowed array where I'm just going to take the number of red dots in each row and the number of blue dots in each column, and those are going to become entries in a 2-rowed array. So notice here, I've got 5 red dots, then I've got 2 red dots, and I want you to pay attention here. There's 0 red dots to the right of the 3rd black dot on the main diagonal. That means I'm going to put a 0 in that location in the Frobenius symbol. So I'm going to have 5, 2, 0 in the first row. There it is. And then when I go back and look at the blue dots in red vertically, 5, 3, 1, and that's where I get my 5, 3, 1. And you have this fact that the weight of this Frobenius symbol is exactly the sum of all the numbers in the array plus the number of columns, which is 3, and that will be exactly the weight of the original partition. And clearly these are in bijection with one another. The Ferrer's graphs and the Frobenius symbols. Very quickly, total side note, Frobenius, one of the reasons Frobenius wanted these symbols is because you can now flip the 2-rowed array very quickly. Just take the bottom row, make it the top row, make it the bottom row, and you will have immediately conjugated the partition, the Ferrer's graph. And so Frobenius was looking for a way to see partitions which were self-conjugate in a very rapid fashion. Okay, I want you to notice that the parts here are now strictly decreasing by the nature of the construction, and it is possible to have a 0 at the end of either row. In fact, you could have zeros at the end of both rows if you wanted, depending on the shape of the Ferrer's graph. So I just said that fact. And in a paper in 2011, George proved that the number of partitions of n whose Frobenius symbol has no 0 in the top row equals the number of partitions of n with odd mechs. Now, I want to just pause and tell you that if you go to this paper in the Electronic Journal of Combinatorics in 2011, I'm 99.99% sure you are not going to find the phrase odd mechs in that paper. This idea of a mex has really arisen in the last 5-6 years. However, if you go interpret what George did, that's the same thing. And so now we know that the number of partitions of n with odd mechs is equal to the number of partitions of n where the Frobenius symbol has a 0 in the top row, but we also know that it's the number of partitions of n with non-negative crank. So all of these 3 ideas are now glued together, and that's what that paragraph says, okay? In our JCTA paper with Dennis Stanton, we extended this result in 2 ways. So the first is this: the number of partitions of n with crank greater than or equal to j equals the number of partitions of n minus j whose Frobenius symbol has no j in its top row. If you take j to equal 0, then this theorem would say the number of partitions of n with non-negative crank equals the number of partitions of n whose Frobenius symbol has no 0 in its top row. So this is a really pretty generalization, if you will, for any j greater than or equal to 0. The other theorem is a little less elegant, in my opinion. I'm just being honest. It says the number of partitions of n with crank 0 equals the number of partitions of n whose Frobenius symbol contains no 0 minus the number of partitions of n minus 1 whose Frobenius symbol contains no 0. And that difference really comes from the shape of the generating function. It's unfortunate, but true. Still a nice result, nevertheless. And we prove these via generating function manipulations. Okay. Now, with that done, let me also take one more side trip and talk to you about the MEX, but I want to split it now. So we looked at MEX odd and MEX even. I now want to take it one step further. So I'm going to define M sub ij of n to be the number of partitions of n where the MEX, that's the smallest missing part, is congruent to I mod j. So clearly, for example, M sub 1 comma 2 of n is just the number with odd MEX. M sub 0 comma 2 is the number with even MEX. Okay. And also clearly, O of n is equal to M sub 1,4 of n plus M sub 3,4 of n. And remember, O of n, the number of partitions of n with odd MEX, has a connection to non-negative crank, and now we know it has this connection to Frobenius symbols that have a 0 in the top row. And then we discovered and proved a really, really interesting connection now when we take the odd MEX partitions and cut them again between 1 mod 4 and 3 mod 4. Namely, for any n greater than or equal to 1, the number of partitions whose MEX is 1 mod 4 equals the number of partitions of n whose MEX is 3 mod 4 when n is odd. And when n is even, you just have to tack on q of n over 2, where q of n denotes the number of partitions of n with distinct parts. This is a really, again, it's not obvious a priori that this is going to happen. And yet with very straightforward generating function manipulations, we were able to see that this is true. And with this in hand, we were able to prove a result very quickly that appeared in another paper of George Anders and David Newman, that one in 2019. And here's what it said. It said that the number of partitions of n with odd MEX is almost always even. And the only times it's odd is when n is twice a pentagonal number. That's what it means for n to be j times 3j plus or minus 1. Well, our proof fits on this one slide, so you know it's short. Here it goes. O of n is equal to M14 plus M34. That's what I've got on the left-hand side. But M14 is another copy of M34 when n is odd. So that gives you the 2 times M34 of n. And when n is even, you tack on the M34 plus Q of n over 2. And so clearly mod 2, you're going to get either 0 most of the time. And when n is even, you get Q of n over 2. But that means that the parity of O of n for even n reduces to the parity of Q of n over 2, but that follows completely from the pentagonal number theorem. And one can write down, thanks to the generating function for Q of n and the pentagonal number theorem, this result. And that's why twice pentagonal numbers appear. Okay, so really interesting, very quick proof, thanks to what we showed with M14 and M34. Okay, I'd like to make another shift really quickly now and talks about some of the results from the paper with Ezai very quickly. First of all, one of the things we did in the paper with Ezai was to go back and prove some of the things in the paper with Brian and myself and Dennis Stanton, but to do it combinatorially as opposed to with generating functions. So that happened. But the other things that we did were really, really cool. And I just want to mention a couple of them to you. First of all, I want to show you this theorem. Now, for those of you who are not generating function people, either generating function lovers or just don't do much with them, I want to just tell you what's going on, especially on the left-hand side. We have the generating function again for the number of partitions of n where the crank is exactly m. That's what the capital M of little mn function is doing. And the outer sum is summing over all partitions, or I should say all crank values greater than or equal to j. So I'm now not just looking at all crank values greater than or equal to 0, with what we did with non-negative crank. Actually now, I'm actually now going to take all crank values greater than or equal to some fixed J. And on the right-hand side, I end up with a really nice single sum with two finite Q Pockhammer symbols in the denominator and just a power of Q in the numerator. The two pieces in the denominator are handling, in essence, a partition to the right of the Ferrer's graph and a partition to the below it, below and to the right of the Durfee square, it's called. And what's really cool about this result is that it's not alternating. There is no power of -1 in this right-hand side. And because of that, we believe that the summand on this right-hand side should be counting something combinatorially. And in fact, it is. And so we were really pleased to see that we could find this generating function result that actually gave us a way to count things without having to add and subtract as we went. Really nice result. And then let me highlight one more refinement that appears in this paper with Esayi. I'm now going to take the Mij function, but I'm now going to split it one more way, namely between whether I have an odd number of parts or an even number of parts. And so I'm going to have superscripts O and E. And then I'm also going to take the partition function into distinct parts and look at the number of parts being odd and the number of parts being even. So in nothing I've done so far today, were we looking at the number of parts. It turns out that we were able to prove the following result combinatorially, namely that the number of partitions with an odd number of parts and MEX, that's 1 mod 4, is equal to, and then you switch over to MEXs that are even number of parts, but the distinct part function has odd number of parts. So this is a refinement of the theorem that I showed you a few moments ago. And then you can do the same sort of thing on the even odd side with the number of parts as well. And we proved this combinatorially in the paper with NYNTS. So it's a great refinement in the process. All right. This
everything,
also led to
everything in the proof. Sorry, everything in the proof is combinatorial. It's all constructive. You can biject between the two sides.
You know, Moshe, thank you for the question. My recollection is that it is. I'd have to go back and make sure.
I mean, some little bits of this could be a generating function logical, even if the whole thing is bijective.
Absolutely, absolutely. So yeah, actually, Moshe, let me say to you, given what we just shared, that there's got to be pieces of this that also have generating function mixed to them. So yeah, I should be careful. I don't think we literally mapped the partitions on the one side to the partitions on the other side explicitly. I don't think we found that bijection explicitly.
All right. Since there's been an interruption already, can I ask whoever is snorting very loudly every few seconds to please mute themselves?
They might be asleep. Someone might need to do that for them.
Kevin?
Yeah, I've asked the moderators to mute, but nothing's happened.
Yeah, the host can do it.
Yeah, I don't know if Mel is able to.
I've been trying to do it, but all I can do is click on something that says ask to unmute.
Ah, okay.
I think if you go to list of participants, you can unmute, mute.
Mel, if you're able to identify who it actually is, you might be able to mute them individually.
Oh, I know. If I could do that, but I'm looking at everyone, but I can't.
It's Kevin Johnson, I'm afraid.
Kevin Johnson.
Yep.
Kevin. Oh, okay.
Sorry.
Okay.
Let me
Huh,
find
okay.
Kevin.
Well, my apologies, folks. I can't do it. So if it's okay by you, I'm going to just push forward. Yeah, and let me pass on this because this is just another example of the thing that we did. So now let me transition today to my last topic on partition fixed points. So in the summer of 22, I saw this paper by Aubrey Bletcher and Arnold Knopfmacher that appeared in the Ramanujan Journal. And they define a partition fixed point to be a partition or to be a part in the of size I that is sitting in the ith position of the partition. And let me remind us now, we're writing these partitions with parts in weakly decreasing or non-increasing order. So any partition you write down in that fashion either doesn't have a fixed point or it has exactly one. It lands in just the right spot. It can't have more than that. I should mention that Bletcher and Knopfmacher actually then think about what would happen in that same paper if you wrote the parts in increasing order, non-decreasing order. And then they talk through what that weighted sum might look like. But in our case, we only have either no fixed points or exactly one fixed point for every partition in question. So let's go back to the partitions of 4. Which ones have fixed points? Well, there they are. The 2 plus 2 has a fixed point in the second position because the second position has a 2 in it. And 1, 1, 1, 1 has a fixed point because the first position has a 1 in it. And the other 3 partitions do not have fixed points. So I hope that makes sense. Notice that there are more partitions here with no fixed points than there are partitions with fixed points. It's a small example, but there it is. And I'm going to let f of n be the number of partitions of n that do have a fixed point, and g of n be the number of partitions of n that don't have a fixed point. These are the notations from Bletcher and Knopfmacher. Clearly, p of n is f of n plus g of n. You either have a fixed point or you don't have a fixed point. And Aubrey and Arnold found generating functions for these two. And they also hypothesized that when n is at least 3, g of n would have to be greater than f of n. But they failed to make the following connection, which Brian and I proved. Namely, g of n equals the number of partitions of n with odd mechs, or non-negative crank. And f of n equals the number of partitions of n with even mechs, or positive crank. In other words, these partition fixed points are exactly the same. They're doing the exact same thing as checking for either non-negative crank or positive crank, or odd mechs, even mechs. And so when n is greater than or equal to 3, of course, g of n is greater than f of n, because g of n minus f of n is the number of crank partitions. This is what I was sharing with you folks several minutes ago. So in essence, this is just Shen's inequality in a different form, but it's exactly the same thing as what we talked about earlier. And I should point out that the first proof that Brian and I had of this was we looked at the generating functions that Bletcher and Knopfmacher had for G and F, and we said, those look an awful lot like the generating functions that we've already seen in our other papers. And so it was pretty easy early on to spot this relationship. So here is my the following are equal type of theorem. The number of partitions of n with a fixed point is the same as the number of partitions of n with a 0 in the Frobenius symbols top row. It's the same as the number of partitions of n with even mechs. It's the same as the number of partitions of n with positive crank. And there's a corresponding set of results. Very proud of my LaTeX skills here, by the way. For not having a fixed point, then you exclude a 0 in the Frobenius symbol. You have odd mechs, not even mechs, and you have non-negative crank as opposed to positive crank. All right. So I remember when I contacted Brian about this, when I saw this paper of Bletcher and Knopfmacher, I said, Brian, we can start listing these kinds of things. This is really cool. And I give him a lot of credit. I really do, because he said to me, yeah, that's cool, James. But I mean, in terms of pushing the technology any further than what we already have, all you did was spot the fact that those generating functions in the paper of Bletcher and Knopfmacher are basically the same as the generating functions we've already seen. And I had to give him credit. He was very wise to say that. So we pushed it aside for a moment, and then we came up with the following generalization, which I really like. Namely, we generalized the idea of a fixed point now to be something that I'll call a K fixed point. Namely, part I now needs to be in position, the ith part needs to equal I plus K. So now we're shifting where that fixed value is, if you will. And for any K, 0, positive, or negative, we can define new functions, f sub k of n, g sub k of n, where you count the number of partitions of n where the ith part is equal to I plus k. In the notation from a moment ago then, f and g would just be f sub 0 and g sub 0. We actually found results for k positive and another set of results for k negative. It turns out that the k positive results are, in my opinion, a lot prettier. And so I'm going to focus on those as we close today. I need one more function. I'm going to call it mex sub j, and it's going to be the smallest integer that's bigger than j that is not a part of your partition. So the mex just looked for the smallest missing part. Mex sub j will now look for the smallest missing part that's bigger than j. So you can now look for various different statistics here. So for example, partition 53331, mex sub 1 is 2. 2 is the smallest thing bigger than 1, and it's the first thing it's missing. But the mex sub 2 in this same partition is equal to 4 because we have 3s, but we don't have a 4, okay? And now I can, and mex sub 0 is equal to the mex that we've been talking about for the last 45 minutes, okay? Very cool. And now we have the following result for any k greater than or equal to 0. The number of partitions with a k fixed point is equal to the number of partitions where the Frobenius symbol includes a k. It's equal to the number of partitions of n where mex sub k minus k is even. Now, this one may not look like it's a really nice generalization, but remember, when k is 0, mex sub 0 is just mex, and minus 0 does nothing. So item 3 is a generalization of having even mex. And lastly, the number of partitions with crank strictly bigger than 0. Well, strictly bigger than k. That would have read strictly bigger than 0 earlier, which would have been positive crank. And you can have a similar result without a k fixed point. You exclude k, you let the mex k minus k be odd, and this is the part I really love. Instead of crank being greater than k, now crank has to be greater than or equal to negative k. So when k was 0, we didn't really notice a lot of difference. Crank was either bigger than 0 strictly or bigger than or equal to 0. Now the crank has to be bigger than some positive number k, or it has to be greater than or equal to some negative value k. And so there's a whole swath of partitions there in between where the cranks are strictly between negative k and k that are not being counted by this characterization, which I think is a really interesting, unexpected result in the process. And so I'm very thankful to Brian for pushing me to think about these new functions, f sub k and g sub k. All right, let me close with this. Tons of work has been done in the last 5 years on this mex and crank. At one time in this talk a few days ago, I literally had a list of probably 15 or 20 papers that have been done in the last 5 years on mex and crank. Not by me, by lots of people. I just decided to summarize it into one sentence. There are still questions to be asked and answered, and let me give you 3. Can we find combinatorial proofs for any of the things that only have analytic proofs up to this point? That's a good question. Can we further refine the mex So we looked today at 1 mod 4 and 3 mod 4. What about 1, 3, 5, and 7 mod 8, for example? Obviously, you can go count these things, but do they somehow relate to some sort of crank, to some sort of thing with F sub k and G sub k with partition fixed points, etc.? I think that's a really great question on the computational side. And lastly, are there ways to to refine fixed points? This is the newest statistic of all of these. And I think it would be interesting to ask, count the ones where you have a k fixed point where k has to be even. Count all the ones where you have a k fixed point where k has to be odd, and so on. We haven't got there yet. And I think that would be a really interesting thing to look into as well. And with that, I will close and say thank you very much.
Thank you. Any questions for our speaker?
Have these led you to any new congruence results? Found any new congruence results from this stuff?
Moshe, that's a great question because I always look for those kinds of things, of course, almost to a fault. Other than the kinds of identities I showed you a moment ago, where I now know that M1 4 is equal to M3 4, and and that these things are congruent mod 2, they have the same parity to the distinct partition function. It's not led me to anything else, certainly not along the lines of Ramanujan's congruences, for example. So no, I say with, it hurts me to say that, but no, I've not seen any congruences.
Any applications to representation theory, character tables?
Oh, that's something I have not thought about at all. And I fear that I don't have the background necessarily to really see what that would be.
I'm pretty sure you've done some stuff on zeros in the character table,
Well, I've done some things with representation theory with my good friend Rishi Nath, who I think I saw a few minutes ago.
He's there.
Okay, so I would have to defer to him, Moshe, and that's a conversation Rishi and I have not yet had. Rishi, I hope you're paying attention. It sounds like we need a phone call fairly soon. I think I see another question, Mel.
Someone has their hand up, but just unmute and ask your question, please.
Yeah, hello, Professor Sellers.
Hi.
Can you hear me?
Yes.
Yeah, hi. So it was a very nice talk. I have a question regarding the generalization of the fixed point. So have you looked at this case where now you lambda I equals some hi plus k, something like that?
Yeah, so we have not generalized the definition of fixed point any further than just this linear shift from I to I plus k. We have not tried to take that further. I could imagine lots of different possibilities. I should say one thing though that I skimmed over. So in the paper, we think about I plus k, where k is positive. We also think about I plus k, where k is actually negative. So the fixed point actually shifts over. I guess you folks might be seeing me doing it in the wrong direction, but it actually shifts over to the left as opposed to shifting to the right. So we do think about both of those shifts, but that's just a linear displacement by k. That's all we do.
Okay. And what did you mention at the end of your talk? Even and odd fixed point. So what was that about?
Well, I just mentioned it off the top of my head. I mean, we have not tried to combine, say, fix a value of n, look at f sub 0, f sub 2, f sub 4, etc. of n, sum those up, do that for lots of values of n. Is that an interesting function? Is it in the OEIS? I have no clue. So we've really not done much more. The paper in discrete math where we do this just appeared on their website, I think less than a month ago. It's in the May 2024 issue. And you can see what we did there near the end of that paper.
Okay, what's the title of that paper?
Look up Hopkins and Sellers. Actually, hold on. Give me 1 second. I can answer that question. If I knew how to use Zoom better, I could answer it even quicker. Hold on 1 second. It is the second one on the screen right now.
Okay, I see. I see. The discrete math one, right?
Yes.
Great.
And
Okay.
it's actually available on the archive as well for anyone who does not have access to discrete math. An older version in PDF form can be found on the archive.
Okay. Okay. Thanks a lot, Professor.
You're very welcome.
Other questions for James?
Actually, so yeah, so just out of curiosity, is there like a known asymptotic formula for the number of partitions with like crank 0, for example?
So Noah, I think the answer is yes. I don't do a lot with asymptotics. What I can tell you is that you can write down a generating function pretty easily for crank 0. Well, so you go back to Garvin, right? He's got a generating function for crank any m. Let m equal 0. You're going to end up with 1 over QQ infinity times that little alternating sum that I showed in red earlier on the screen. I have to believe you can get an asymptotic from that, which is basically going to rely heavily on the Hardy-Ramanujan formula for P of n. Does that make sense?
That does, yeah. I guess I was sort of curious, like if the partitions with like odd mechs make up 50% of the partitions in the long run, or if it's like there's a slight bias towards them. Yeah, if you could, I guess, show that that has like density 0 or non-zero or whatever.
Right. So we know that partitions with odd mechs minus partitions with even mechs is exactly crank 0. So odd mechs is going to beat even mechs for all n actually greater than or equal to 3, but whether it in the limit it goes 50-50 or not is, yeah. I'm going to be quiet, Noah, because I feel my foot coming up to my mouth. I feel like mathematically I'm going to just say stupid, so I don't want to do that.
Probably
Thank you for your
50-50.
thoughts.
Probably
Oh.
50-50. Because crank 0 is too thin. Because crank can be, very big.
Makes sense. Thank you.
Thanks, Dennis. Thank you.
Other questions, comments, theorems, proofs, conjectures, problems, political prognostications? So oh great, okay. All right, James, thank you again. It was very, very, very nice talk. Next week's speaker is speakers are David and Gregory Trunovsky, talking about the telephone gossip problem and homage to Richard Bumby. So we all look forward to that. Let me remind you or inform you, I haven't done anything on paper yet, that the CANT conference for this year is, as always, before Memorial Day, the Wednesday, Thursday, and Friday before Memorial Day, which is May 22 to May 24. And it will be, as it was last year, a hybrid conference. So there will be 3 days of meetings in the Graduate Center with the associated wine, cheese, and problem sessions, But everything will be on Zoom, and there will also be talks on Zoom that will, so the whole conference will be on Zoom, and speakers will be wherever they want to be, either physically present in New York or physically present somewhere else in the world. And I am in the process, many months late, of putting together the proceedings of the last conference for Springer. So it never happens that the proceedings of year end actually appear physically in book form before the conference in year end +1. But at least I will know that it's in the Springer production system, and I'm done with it. So that's almost done.
Thanks
Okay.
again, Mel, and thanks to everybody who was here. It was great to
Thank
be able
you.
to speak. Thanks so
Thank you.
much.
Thank you, James.
Thank you. Thank you. Thank you, Mel.
Thank you. David, did you know Vershik?
Well, I met him on on our seminar.
Okay. Okay.
Yes,
Yes.
I knew of him, but in 3D I met him on the seminar.
Okay. No. All right.
Thank you, Mel. Be well.
Thank
See
you.
you.
You too. See you and listen to you next week, David.
Thank you.
All right. Okay. Bye, everyone. Be well.
Bye.
See you next week.